All right, so last day we talked about indicators. We talked about litmus and methyl orange and phenolphthalein. Today we're going to talk about titration. So this is your lab number 7. So I don't think you did your lab this week. You'll be doing it next week. And in your lab next week, you will be doing what's called a titration. So this slide says, how do we find the concentration of an acid in real life? So you can use indicators, but an indicator is only a reference pH, meaning like it's going to excuse me, it's going to give you an idea of if something is an acid or base, but it won't necessarily tell you the exact concentration. So what we do is a titration. This is a method used to find an unknown concentration. It's straight up review from Chemistry 1120. So like what I'm going to show you today, you've done this before. It's basically using a neutralization reaction and stoichiometry, if you remember that word. Maybe it's not your most favorite word. It can be a little complicated, but we're going to use this to figure out the concentration of an unknown reaction. So the way a titration works, and you'll see this in the lab next week, this is one of the few times in this course where you'll actually do the lab after the course information, but you will see this in the lab. You use this setup where you have 2 pieces of glassware. You have a burette. It's called a burette. And this contains your base, or it could be your acid, but basically it contains the chemical that you know. And then below that, you have the Erlenmeyer flask, which contains your unknown. And you basically mix them together until they are neutralized, so you can find the concentration of that unknown. So how do you know when you're doing a titration, how do you know that it has been neutralized? Well, we use phenolphthalein or an indicator. And there's two definitions on this slide, and it's really important that you know the difference between the two of these definitions or terms. When you're doing the titration, there is an end point and an equivalence point. So the end point is when the volume has, you've added your unknown, you've mixed the chemicals together, and your indicator changes color. And in this case, and in your lab, and anytime in 1121 when you're thinking about a titration, your indicator will be phenolphthalein. So phenolphthalein, like we talked about yesterday, let me just go back a couple of slides. This is an indicator that turns pink or light pink almost near 7. You'll notice it's not perfect. Its range is around 8.2 to 10. But the idea here is that almost around 7. So when your solution is becoming neutral, it will start to change color. And that is what we would call the end point. The equivalence point is different. This is the most important part. This is the volume where your moles of acid and your moles of base are the same. So you've effectively neutralized, and let me write that down. The chemical. So again, this is kind of hard to imagine or hard to kind of picture in your head, but you will see this in the lab next week. You're going to mix an acid and a base together. And you're going to personally look for the end point where the solution changes color, but what you're actually calculating is the equivalence point, and that's where you have neutralized the solution. The moles of the acid and base are equal. And it mentions at the bottom of the slide here to choose an indicator where the endpoint and equivalence point are approximately the same. And there's not really some magic indicator that does this. So we typically use phenolphthalein in the lab. So around 8, around 8.5, it starts to change color. That's pretty close to the equivalence point. Yes, you do need to know this. So I'm just reading a comment in the chat here. So let's look at this problem. Let me just, okay. All right, sorry. I just wanted to skip ahead and see your questions. So let's look at this problem. Now, the problem has already been completed in the notes, so I will do this with you. This is a reaction between hydrochloric acid, HCl, and sodium hydroxide. So kind of like your most classic acids and bases. You'll notice in the balanced chemical equation, so this has already been balanced. It's 1, 1, 1, 1. So every chemical here is, it's balanced, and there's one of each. So this is the titration where we're taking 10 milliliters of our unknown. Let me just erase the text here. And we're mixing it with our known. The known, like when I say known, I mean it's the chemical that we have the volume and concentration for. So step number 1, find the moles of the chemical that you know. This is the same as what you would have done in chemistry 1120. So again, this is not anything new. You've done this before. You would find the moles of the chemical that you know the information about. In chemistry 1120, you would use the formula moles equals mass over molar mass or something like that. Well, in 1121, we're dealing with acids and bases, and in particular, we're dealing with solutions. So you would use the formula concentration is moles over volume. You can see this formula here. This formula is, of course, in your data book. So step number 1, find your moles. Pretty easy. Moles equals C times V. I just rearranged this equation. Okay, again, you really need to be comfortable in this course with rearranging equations. So moles equals concentration times volume. So I take my known, and step number 1 is to find my moles. So I multiply the 0.1 moles per liter by the 23.49 milliliters. One thing before I move into the next slide is notice we converted milliliters to liters. We use liters in this calculation. So I divided that number by 1,000. That's how I got the liters. Okay, so that's step 1. Find your moles. Concentration times volume. Don't forget to change your volume to liters. Step 2. This is the step that I'm most worried about. This is review from chemistry 1120. So you've done this before. In step 2, you use your mole ratio. So now that I know the moles of NaOH in this reaction, I can also calculate the moles of HCl. These chemicals are 1 to 1, meaning that I would use 1 and 1 in my mole ratio. I kind of hope you remember this from Chemistry 1120. So to find my moles of hydrochloric acid, I multiply that number of my moles of NaOH by the mole ratio, and I get my moles of HCl. Now, because this reaction is 1 to 1, meaning I have 1 mole of HCl for every 1 mole of NaOH, you'll notice that the number doesn't change, and that's normal if the ratio is 1 and 1. All right, there's only one step left. This is a 3-step problem. I'm looking for the concentration of HCl. So step number 3 is I need to actually answer this question and find the unknown. So I use my equation. Concentration is moles per liter. I know the moles of I know the moles of HCl. I also know the volume of of HCl. So I divide the two numbers and I get my answer. Pretty straightforward. If you're confused or you don't know what to do, I'm going to show you an answer on this page. But before I do that, I would love to give you guys a minute to try this on your own. So before you try this on your own, just let me write the steps here. So step 1, you want to find the moles of KOH. Step 2, you want to find the moles of H and O3. And step 3, you want to find the concentration of H and O3. The formulas that you need, or the formula that you need, is right here. Oops. Sorry. There we go. So I'm going to give you guys a minute to try this. If you don't know what to do, that's fine. I'm going to show you how to do it, but I would love to give you guys a minute or two to try this question. So I will be back in, let's say, 2 to 3 minutes, and we'll check your answers. Okay, so good luck, have fun, and I hope you can get the answer. Okay, so let's look at I have an answer or two in the chat here. It's pretty quiet today, but that's cool. So let's look at this and check your answers. Now, I know the answer is here. You can see it in red, but let's do it together. Let's pretend that I haven't done this before. And let's see if we get the answer. The answer, by the way, is 0.22. So let's see. Let's try this together. Let's try this together and see if I get the answer. All right. So step number 1. Whoops. Sorry, my wrist hit the keyboard. Step number 1, find your moles of your known. Your known is the chemical you have all the information about. So I'm going to find the moles of KOH. So what I do is I multiply the concentration times the volume. So if the formula is C equals N over V, my formula for moles is C times V. So 0.4502 mole per liter times 0.01264 liters. Now, again, some of you might be wondering where that number comes from. I changed my milliliters to liters. I mean, in theory, you don't actually have to do this, but you should do this. Okay, so where's my calculator? Here it is. Let's check this out. Let's see what we get. So 0.4502 times decimal 0.1264. And I would get, now my calculator is giving me scientific notation, but I'll write it as a decimal. I get decimal 0.569, let's say 0.5 moles. I'm going to write a couple extra significant figures. I can only have 4, but I'll write an extra one just in case. All right, and I get another answer there. Yasmin just gave me her answer for, looks pretty good. All right, so let's see. Step number 2. Use what's called the mole ratio. So I know the moles of KOH. I want to know the moles of HNO3. So I take my number, and I multiply it by my mole ratio, meaning the numbers in front of the balanced chemical equation. So in this case, again, luckily for us, 1 mole of HNO3 is equal to 1 mole of KOH. It's the same number, so I get my same answer. All right, last step. Step 3, find your concentration. So concentration is moles over volume. So I write my moles. Oops. Now, one thing that's important, you'll notice that I'm using 25 milliliters here because the volume of my acid was 25 milliliters. So just be careful in this step. Make sure you use the correct numbers, and let's see what I get. And yeah, so what I get on my phone or my calculator is decimal 22762 mole per liter, or what I would write is decimal 2276 moles per liter. Again, with significant figures, I have 4 numbers, so I would keep 4 significant figures. So there you go. We could calculate the pH of this if we wanted to. We don't need to, but there you go. That's our answer. So decimal 2276 or decimal 228, whatever you want to call it. There's my answer. All right, cool. So that's it. How do you guys feel about that? Are there any questions about pH? Or sorry, not pH, about titrations. Sorry? No questions?
Yeah, I said no question.
Okay, perfect. All right, now, I have 2 slides left for this section, and then we'll get into the last section. Two things I'll mention is in a real experiment, not in the course or not in, like in your notes, but in a real experiment, you don't just do one titration. Okay, so when you're in the lab this week, or sorry, I guess not this week, it's Thursday. When you're in the lab next week, you will be looking at titrations, and you will be doing maybe 1, maybe 2, maybe 3 titrations. I think the way the lab works is you have to do it at least 2 times, and maybe a third if you have an issue. So just one little note here, if you're, for next week in the lab, or you're doing this in real life, you never do just one. You always do multiple trials, and then you would calculate your average. So this, you don't need to study this or anything, don't worry, but just keep in mind that when you're in your lab next week, you're going to do multiple titrations and calculate the average. The last thing I'll mention about titrations is, they can be very stressful. This is like I guess a meme or something. They can be very stressful. You can see like the heart here in the last image is going crazy. Take your time, relax. You have enough time in the lab to do them. They're very delicate procedures. You have to be very, very careful. It's like holding a baby. You have to be super, super careful. And you'll see this in the lab next week. I'm kind of excited for you to do the lab, and I wish I could be there, but unfortunately with COVID and everything, I won't be there. But I am excited for you guys to do that experiment. All right, so the finale of today. Oh, okay. I'm gonna have to do something a little different here. I don't have my notes downloaded to the computer, so I'm gonna go on D2L. For the finale of today, I just want to introduce, as always, the next section, and then we can finish that on Monday. So guys, just remember, we're basically done chapters 3 and 4. I mean, there's really not much left. So you guys are basically ready for your test next week. I will need to take a little time on Sunday to finish chapter 4, just 15 minutes or so. But we're done the chapter. So we're going to keep moving on with the course. I will have a review next week, a tutorial, but you can basically consider ourselves done with chapters 3 and 4 today. There's only one little part left, which I'm going to introduce right now. If you guys just give me 5 minutes, and then we'll finish it off. So the last part of chapter 4 involves something called buffers, which is a lot easier than it sounds, and equilibrium for soluble compounds. This does sound a little complicated, but it is actually pretty straightforward. So just give me 5 minutes here to introduce this, and then we're done. So I don't know if you've heard this in your lab. I don't know if Miss Michelle mentioned this, but buffers are a mixture of weak acids and their own conjugate base. This, actually, guys, let me be real straightforward with you. This is a huge wink, wink question. This is typically a multiple choice question that I've asked in the past on, a final exam or something like that. I say, what is a buffer? A buffer is a mixture. It's a chemical, it's a solution, and it's a mixture of a weak acid and its own conjugate base. Whoops, let me get my mouse here. So that's like the scientific definition of what a buffer is. No, that's not true. Not the scientific definition. That's kind of how you would make a buffer. It's a mixture of a weak acid and its conjugate base. So what is a buffer? A buffer is a chemical that resists changes in pH. And all of us, everybody here, so the 20 or so students in class and myself, we all have a buffer inside of us. A buffer is any chemical that resists changes to pH. Oops, sorry. I forgot I wasn't actually using PowerPoint. So think about your body and how delicate I'm going to say ecosystem, how delicate your body is. You eat a lemon or you eat some baking soda. How come your body's pH doesn't change? there's actually some, myths out there. People say, like, if you eat an alkaline or basic diet, you will be healthier and all this nonsense. That doesn't make sense, because your stomach is full of hydrochloric acid. So your stomach is full of concentrated acid, and nothing you eat will change your body's pH. It's impossible, unless you're very sick. Your body has a way to resist changes in pH. More specifically, the blood in your body comes with its own buffering system, I think it's hydrogen carbonate, or carbonic acid and carbonate, where you have a weak acid and its conjugate base that will resist changes in pH. So that's what a buffer does, and they're all in your body right now. So an example of this is a sodium acetate buffer, where you could take sodium acetate. This is the first chemical here. And you could take acetic acid and sodium acetate, and it basically neutralizes pH changes. So, for example, if you added a base to this buffer system, the acetic acid would react with it. If you added an acid to this system, the sodium acetate part, the base part, would react with it. So it fights pH changes by reacting with acids and bases. This is the one I was talking about in your blood. It's a bicarbonate buffer. So you have a weak acid in your blood, carbonic acid, and you have a weak base in your blood, hydrogen carbonate. And when something gets into your blood that might want to change the pH, for example, if it's an acid, the weak base reacts with it. If it's a base, the weak acid reacts with it, and it neutralizes those changes. So I think I'm going to stop here for today. We'll get into solubility on Sunday. What time is it? 12:13. Yeah, I could do this, but I think I'm going to stop for today. Let me just check the chat. There's a couple comments in there. Ooh, some good questions. Okay, so let me just read the chat before you all leave me and enjoy your weekend. Let me just read the chat to you. So Abdullah mentions, can we review on Tuesday? I think what I mentioned yesterday is I might have a tutorial, a test tutorial on Wednesday evening. I think we're getting close to the end of the course, and I can't really use too much class time. So I'm going to have a tutorial outside of class hours in the evening, and that will be Tuesday or more likely Wednesday evening. It's totally optional, by the way, and I will put the recording up on YouTube. Then Aman asks, are you going to talk about the test, like how many questions? I can let you know that on Sunday. I'm going to make the test this weekend. I haven't made it yet. So, Aman, if you could remind me on Sunday to let you know about the test, like how many questions, what type of questions, let me know on Sunday. Nor asks, what is the meaning of conjugate? Conjugate is a Latin word that means pair or partner. So I do apologize if you weren't here for the beginning of chapter 4. In the beginning of chapter 4, if you go back and look on YouTube, we talked about conjugate, acids, and bases. So if you really don't know what conjugate means, check out your earlier notes. But since you're here right now, conjugate just means partner or pair. So in science or in chemistry, it means that they are related. So when I say a weak acid and its conjugate base, I mean it's an acid and its partner base. It's the base with the proton removed. Whew. And then Iman says, since there's an acid in our body, we don't melt or die. That's a really good question. So the acid in your body, this is a question from Iman, the acid in your stomach is an incredibly strong acid. It's hydrochloric acid. So your stomach is filled with an incredibly strong acid. But we don't melt or die because for some reason, we are biologically amazing creatures, right? So your stomach has a lining in it. I think it's mucus, which sounds really gross, but your stomach has a lining or a protective coating that doesn't let the acid hurt you. And if you've ever eaten some spicy food or you're a little sick and you get the feeling of heartburn, you can kind of feel a burning in your chest. That's your stomach acid kind of leaving your stomach and getting into where it's not supposed to be. So I'm not a biologist. I can't even name the parts of your body that this happens to, but when the acid leaves your stomach and rises up and you feel that burning sensation, it's because those parts of your body do not have the lining that your stomach does. Yeah. So like Aman mentions, when you're vomiting, you feel burning. Exactly. When you vomit, when you have heartburn, that burning is your stomach acid escaping. It's not where it should be. And funny enough, I'll kind of end it here. When you do have heartburn, you feel a burning in your chest, your stomach isn't feeling well, and you take a Rennie. If you're anything like me, I always have Rennie around. Um, Rennie is just a base. All Rennie is a base. I don't know what base it is, but it's just a basic compound. And when you eat it, it neutralizes the acid. So very interesting. Body, like I wish I knew more about biology. I used to. I studied biology in university, but I don't remember it now. But your bodies are amazing. Like if you think about the buffers in your blood, the acid in your stomach, the electrochemical reactions like electricity happening between your neurons. I mean, the human body is incredible, but unfortunately, I don't know enough about it. I used to, but it's been, I'd say, 20 years since I studied that. Okay, so I'm going to stop recording. If you guys got any questions, let me know. I will answer more questions about your test on Sunday, and we will have review next week, I promise. Excuse me. So if there's any questions, let me know. Other than that, have a great weekend. Wear a mask, wash your hands. You know the drill. I'll see you later. Keep safe, everybody.